Next, we're going to take a look at the halting problem and show that it is undecidable. So far, we've talked about it being undecidable, and we have suggested that, well, in order to determine whether a particular algorithm or program terminates, we just have to simulate it, and the problem is that simulation may not stop. That's not really a proof. Here we're going to provide an actual proof that there is no way to determine, in general, whether a given Turing machine will halt or not. So let's begin by restating the problem. Here's our language, A sub tm. The strings in this language consist of two parts. The first part is M, the description of a Turing machine, and the second part is a string W. And that string is in this language, ATM, if M is a valid Turing machine and if M would accept W if it were run on W. This set, this language, is undecidable. We can't have a decidable algorithm to find out whether a given string is in this set or not. The only way to know is to run the machine on W with our universal Turing machine, but of course if we run it, it might not terminate. Okay, so that's an informal argument that this language is undecidable, and now we need to come up with a formal proof that it really is undecidable. Just because a simulation won't work doesn't mean there's not some other way to figure out whether M would halt on W. There might conceivably be some other algorithm. Simulating M on W might just be a bad idea. So we need a real proof, a valid proof, that the set ATM, the acceptance problem, or the halting problem as it's called, is undecidable. And our proof is going to work like this. We're going to assume that this set is decidable, and then we're going to reach a contradiction. So if we assume that the set is decidable, then there is an algorithm to decide it. There is a Turing machine or an algorithm. So let's call it H. H stands for halting. It solves the halting problem. This is a decider. This is an algorithm that will always terminate. So if you apply H to a particular string, in other words, you apply H to some target machine and input string, then this algorithm that we're assuming exists, but which, of course, does not, we're going to reach a contradiction. But assuming it does exist, it would either accept or reject. If M accepts W, then H will accept. If M does not accept W, then it's because M will reject W or because M will loop. But if it does not accept W, then H will not loop, it will reject. So such an algorithm doesn't exist. We're headed toward a contradiction, but we're assuming that this language is decidable and that such an algorithm does exist. So we're going to use H to build a new machine called D, which I call the devil machine. D stands for devil. It's a little bit tricky to understand what this machine does. But we're going to use it to construct D, and then we're going to run D, and we're going to come up with a contradiction or a paradox. And we're going to see that D can't exist because it doesn't. We'll see the contradiction. And then we'll conclude that our assumption was wrong, that H does not exist, that there is no decider for the halting problem. So let's get started and look at it in more detail. So this devil machine and the contradiction we reach is a little bit tricky to understand. So I want to begin or go back and make sure we understand what H is. H is the decider that we're assuming to exist that can decide the halting problem. In other words, H is an algorithm that when given a Turing machine and a particular input, it will tell us whether M will halt on that and accept W. If M will accept W, then H will halt and accept. So it does what M does. And on the other hand, if M does not accept W, okay, then H will reject. In all cases, H is a decider, so it halts, it never loops, even though M itself might loop. If M loops, then by definition M does not accept W. If M rejects, halts and rejects, it doesn't accept W either. But H won't loop. H will terminate. H will halt. And so it is a decider. Now let's move on to our devil machine, D. H takes two inputs, or it takes a string that combines two inputs, a machine and an input. But D takes just one thing. It takes the description of a Turing machine. So what does D do? D takes as an input the description of a Turing machine. It could be any Turing machine. So the input to D is a Turing machine. And what does D do? Well, E calls H as a subroutine, and it runs the halting decider as a subroutine. And D is passed the description of a Turing machine. What it does is it runs H on that. And it says, would that Turing machine accept if it were given a description of itself as input? Okay? So H is given the description of a Turing machine plus a string. And what D is going to do is provide that as the string, as the target string, the description of M itself. So if M were run on a description of M itself, what would it do? Would it accept or not? And then what the devil machine is going to do, because it's a devil, it's going to do the opposite. If H accepts, D will reject. If H rejects, then D will accept. So D does the opposite of what H does. D applies H to a Turing machine and asks whether that Turing machine would accept if it were given a description of itself as input. And then whatever H says, D does just the opposite. So here's a recap of what D does. It just runs H. When passed a machine, it runs H, and it asks whether H, and H asks whether M would accept it provided a description of itself. Given a machine M, our devil machine asks whether that machine would accept when given a description of itself as input. And then D does the opposite. So when passed a machine M, D will accept if M does not accept its own description of itself. And D rejects if M would accept when given a description of itself as input. Okay? Now comes the paradox. We run D on a description of itself. Okay? So look very carefully at this definition of what D does. D is passed the description of a machine, and if that machine does not accept when provided with a description of itself, then D accepts. If M accepts, then it rejects. So when we run D on itself, okay, what I've done is I've just replaced M here with D. So now we're running D on a description of D itself. So I've replaced M with D here. Okay, M with D. So now what does D do? It accepts if D does not accept on input D. And it rejects if D accepts. So there's a paradox. Okay? D accepts if D does not accept. D accepts on a description of D if D does not accept on a description of D itself. And D rejects if D accepts. So it's a paradox, such as this next sentence is true, the previous sentence is false. Something's wrong here. And what's wrong is that our assumption was invalid, that the set is not decidable. So let's try to say it again. H, what does H do? Passed a machine description in the string. It accepts exactly when M accepts W. And so now D rejects on a description M exactly when M accepts on a description of itself. And so substituting D for M, in other words, running D on a description of D itself, D rejects exactly when D accepts. So there's a contradiction there.